Hi everyone, I'm Wang from Boston University. I'm very happy to present our recent work about the large-scale holographic particle 3D imaging with the beam propagation model. Particle 3D imaging problem can be stated as we use a plane wave to illuminate particles and capture the scattered field by a detector. Then we image particles from this single captured hologram. It has been widely used in a lot of areas, and we can say it's a challenging problem because it's severely ill-posed since we want to estimate a 3D volume from a single 2D environment, and we have to deal with the challenge of the multiple scattering with the increase of the particle density. There have some studies try to solve this problem, but there are some limitations like the single scattering assumption, the large computational costs are still not solved. In our work, we try to solve all these problems by using the beam propagation model to account for the multiple scattering, and then using an iterative reconstruction algorithm to image the particles in the 3D volume. First, we use the beam propagation method to simulate the multiple scattering. The beam propagation method approximates the 3D object as a series of thin slices along the optical axis, each modeled as a 2D face mask separated equally by a uniform medium with distance delta z. The field is then computed by a sequence of diffraction and refraction operations. The objective function is then used to measure the differences between the computed hologram and the captured hologram. Then, Fista-like algorithm is used to reconstruct the particles. Next, we demonstrate the accuracy of beam propagation method by analyzing both the histogram and the spectrum. As we can see, the simulated histogram and spectrum are close matched with the experiment. The contrast is also calculated. Compared with the first-born approximation-based method, the accuracy is increased by 9 times. We further evaluate how the beam propagation model performs under different conditions like change the diffraction distance delta z, the refractive index contrast, and the density of the particles. We conclude the formula to describe how the beam propagation model accuracy changed with these factors and found that it's inverse proportional to the scattering potential of the 3D object. Next, we image the 3D particles with the iterative algorithm as mentioned before. We first demonstrate the efficiency of algorithm for the simulated hologram, and we can see the algorithm can accurately image 3D particles. We also quantitatively evaluate the accuracy of our proposed algorithm by using the T-color index. As shown in this figure, we can image 3D particles with a T-color index as high as 0.9 for the particles with high density and refractive index contrast. The comparison between the BPM and the first-born-based method is shown on the right, where we can clearly see our proposed method can image particles at a deeper depth, where the first-born-based method failed. Finally, we verify our method in the experiment. As shown in this figure, our proposed method can successfully image particles, and it performs better than the first-born-based method. In conclusion, we propose a novel algorithm which can image particles under strong scattering effect from a single intensity hologram, and the computational cost is also low for a large-scale problem. I'd like to acknowledge the members of Boston University Computational Imaging System Lab. Thank you for your listening.